Okay, let's get started. Thank you for coming. I know this session, I want to be at 2 other talks at the same time in addition to this one. So I appreciate that you came here to listen to what's a rather actually boring topic. And that's kind of the point. Because there's a lot of parsing jobs that should be easy. They should be boring. You should just be able to get what you want and just forget about it, not worry about something more interesting. But it turns out, at least in my experience, to be sort of deceptively hard. So I'll talk about why some of the sort of best coding practices actually prevent us from solving this problem and how to carefully break them to get a solution, and then I'll tell you about the library that is not out yet, but it's getting far enough along, so I'm enjoying using it myself at least. So why is this hard? So we have some input data and we need to extract out the bits that we want, and it's probably text coming in, or maybe it's some binary format. So for a little bit of background, the kind of parsing I'm doing, by the way, is this text readable to you guys in the back? Okay, you say yes. Okay, I'm actually a neuroscientist. I study small model organisms, and we use lots of instruments that spit out tons of data about what animals are doing or what their brains are doing or so forth. And pretty much every single tool that you use is going to spit out some different format, and then trying to make sense of it, aside from doing it by hand, is actually a rather big task. And so we want to know what the data means, and that we don't know, and that means we want to do exploration. And if you're going to do something in an exploratory fashion, as you guys know from using the REPL, for example, it's really helpful to have fast feedback, right? If you just try something out and you hit enter and then you wait and wait and wait, it really disrupts the flow. So it would be nice to be fast, and I use Scala a lot for data analysis, so this is how things go for me fairly often. So I think, well, I wonder if worms have trouble as they get old sequencing their behaviors, right? There are these action patterns where they do one thing and another thing and another thing. And so I'm thinking about science, right? I'm thinking, okay, I want to look at the probability of these transitions. And so okay, all right, so let's compute these, and so I need to read my behavioral data, and okay, I'm going to parse it, and then I wait for a little while, and then what? There's a stack trace and the parser's broken? What? This is not what I was expecting to be the hard part. I was expecting to be thinking about the science, and I'm thinking about, I can't even read my data. So what's going on? Why is it deceptively hard? It ought to be easy, even though if you look at an absolute level, input is often fairly complex. But we're really good at this sort of thing as humans. We're talking to each other all the time, and we handle all sorts of exceptions and broken rules in language all the time, and it doesn't faze us. So we're good at explaining what we want, and so parsing should be easy, right? Humans are good at this, and we're good at telling each other what we want, like, I before E except after C type of stuff. The problem is that any rule can go wrong, and it needs handling of some sort, or you're going to get garbage and not even know it. And we're not so good, or at least I'm not so good, at intuiting how to get all of those errors through in a smooth, effortless, fast way. And so the hard part about parsing is you need to focus on errors. And that's not where you want to focus. You want to focus on the complex input, which is hopefully not that complex, right? I'm talking about parsing tasks which aren't really difficult. Like you've got this big grammar and you're trying to wrap your head around, is this even, is it even unambiguous how to parse this thing, et cetera, et cetera. For that, you want to use, something which maps reasonably well to BNF or something like that. But a lot of times you just know what you want. You know it's there, and you can see how to get it. And so the question is, how do you actually get it? So, for example, the problem comes up here. If you want to get the head and the first and last element of a list and pull them out, right? This is what you mean. So you take your list and you get the head and you get the last element, right? Easy. But it's wrong because the list might be empty or be a singleton. And if it's a singleton, you may or may not want to separate the two. But here we've decided, all right, as long as it's not empty, well, the head and the last can be the same thing, and so we pull it out like this. But that got a lot harder, right? The code got a lot more complicated, and it's not as easy. It's still pretty easy. It's not such a big deal. But all of parsing is kind of like this. Anything can go wrong. A number can be wrong. Something can be the wrong length. The parentheses don't match up, and the quotes aren't closed, and so forth. And so how do we deal with this? Okay, so what we would like is to be able to focus on the information, on pulling out the parts that we know are there. We'd like to capture errors, so when we have done this wrong, we think we know what to do, but either we did it wrong or the data is wrong. We have some clue of how to proceed. It'd be nice if it was not too slow, and it would be nice if you can achieve these things without having to keep a lot of things in mind. You just do the obvious thing and it works, and it's not going to stop the JVM and so forth. Okay, so to test out some ideas, I'm going to try to parse this world's simplest language here. The only thing that the language can consist of is either letter Y or the letter N. That's the entire language. There's no repeats or anything, okay? So this is as simple as you can get unless you're degenerate. And so if you do this in sort of the standard Java style, you say, okay, we're going to parse, will fit in a character, so we'll parse a character. If we get a yes, we'll say, okay, yes, it's true. We'll map it to true. If the N will map to false. And if we get anything else, we'll throw an exception. Okay, unfortunately, if you then try to use this, and here I will use my handy pointer substitute. If you try to use this, you see I've called this call here, and I didn't catch the exception, right? I wrote kind of the obvious code here. I'm sort of looping through this whole string, parsing out the individual characters and mapping some to 2s and others to -1s, and was this right? Is this wrong? I have no way to even tell from looking at this code if this is what I intended. So what goes wrong also is I'm going to show these graphs a number of times. So on this axis, you'll see the fraction of your data which actually has an error in it. And on this axis, you'll see the slowdown in your program from having to deal with processing those errors. Okay, so ideally, you want to be around 1. That means the errors aren't costing you anything extra. And I seem to have plugged the wrong thing in here. It was supposed to just be the exceptions line. But if you look at the red exceptions line, you see if the fraction of errors is extremely tiny, then on a very simple problem like this, you're spending most of your time on the errors. But if the error rate creeps up to like 1%, suddenly you're spending 10-fold more time than you want just because you're doing this error handling. So that's not exactly ideal. So fortunately, so the failure cases are slow, the success cases are fast, and then we have this problem about did we actually catch it? Okay, so we know how to solve this problem. We use monads. So for example, option. So here, we just did the same thing, but we put it in an option. Unfortunately, the code to parse it looks a little more complicated. And you say, well, okay, but it is more complicated. There's an error there. We need to handle it. And I agree. But this boilerplate grows linearly with the number of things that you have to deal with. And so for something like this, it's not such a big burden. But for cases where you have like 10 different inputs and you're trying to pack them into 2 different data structures and stuff, there's just, you get options all over the place. And you probably don't even want options because that's not telling you what went wrong. So you probably want eithers or some validation construct. And so that is a problem. And then the other problem is, the other thing which is not ideal is that you can see that there's a performance penalty associated with this boxing in option, for example. It's not huge, that's a factor of what, 2 or 3 or something. And this is a super simple operation. This is like, one conditional jump. So, okay, but our success cases are slow, and that's not ideal either. And so the question is, maybe we can just rescue options from the increase in boilerplate. And so what you would like is, suppose you have something complicated like this wiggle class where, it's the experimental animal I'm looking at is wiggling, and it's got some reference to some longer part of the thing called a dance, and it's got an integer for the ID and when it starts and stops and various other stuff. Okay, and we'd like to take some text data and pack it in there. Okay, so we would like to just do it. We just like to stuff the things in. Yes? I'll try. How's that? Okay, so what we would like to do is just parse each piece and plug it in and then be done. And so what you've got is for comprehension with a whole bunch of nuisance variables. And if you keep this and do it through several layers of code, you have to maintain these error types all throughout your calls. So, okay, wait a minute, that's not where I was going. Okay. So maybe we can abstract away the boilerplate. If you were in Miles' talk, yes, you can abstract away the boilerplate. But it's not all that easy to abstract away the boilerplate, because if you have something, for example, you have a function which goes from 2 variables to 1, you'd like to be able to take some sort of exceptional type and propagate those exceptions to the result in this fashion, right? You don't want to have to think about it when you're writing the function originally. You just want that transformation to happen automatically. You kind of pull the error out of the construct. So if you try to do it with sort of a vanilla thing, no framework, then you have to make sure you have some sort of construct that will build it, because it's hard to capture constructors. And then you need to abstract over arity, because that's not built in. So you got to run for 2s and 3s and 4s, and then you might have to do it over your error, abstract over error types. And then we have to abstract over certainty, because some things you might actually know, right? There might be no error there. So you have to do all the Booleans on-offs, at least implicitly. And then finally you can do something that, if you can convince the compiler that all the types work out, looks pretty short. But you still end up with those performance penalties, and you end up with a big cognitive burden of maintaining all of this idea about what can work and what not, and what is boxed and how, and different types of boxes. And sometimes that's exactly what you need to keep the problem straight. But a lot of times with something like parsing, it's not. You just want to have an idea that the data here is problematic and toss it or set it aside and keep on with the good stuff. So it seems like we want something more like exception. So of course people have dealt with these sorts of error conditions lots and lots and lots. And so the return values, if you build some contraption around your return value, you slow on success, and you've got boilerplate, and your logic is mixed in. If you have exceptions, it's slow on failure. Now people have used error codes; these are fast, but you forget them. You will forget them. I forget them all the time, so that doesn't work. And you could use goto too, but that seems like maybe a bad idea. So all right, what about error codes? Do they really work as you think? And so here, basically, yes. The logic, if you write the little error code handling thing, which maintains little internal error state for that simple language, and compare it to what you can get as fast as you can by hand, it's the same thing. So okay, they certainly work, but we won't remember them. So. And then what about goto? How if we had goto, how good or bad would that be? So we can do this in C. This is like, I think this is like the most dangerous library call, pretty much in the standard C library, is a set jump, long jump thing. But it's really fast. It doesn't take many clock cycles to store that state and to jump back to it, because you're just doing it so dangerously. And the JVM doesn't have it, which is maybe nice, but it'd be nice to get as close to this as we can in a sort of safe way. So that we can do with stackless exceptions. So there's a problem. So if you guys can see this code, so there's a break in the Scala control, Scala util control breaks thing. There's this break command, and that uses a Stackless exception to jump out of a closure. And so here's some code, which if you know how this works, you might realize that this is a problem. So what if you run this thing in the REPL? What do you think the answer is? So it turns out that the answer is that, which really isn't very nice. Failure mode. So the problem here is that this break is supposed to go inside a breakable construct. And then you get this bare exception just propagating up the stack until it falls in your face. Okay, that's not so good. But the compiler also does these with non-local return statements, and they just work. It's like magic, unless you put them into a future. So assuming we can keep that straight, and we already have to, we'd like some other tool that can do the job. And the reason is that in simple cases, it's as fast as using error codes. There's no penalty for doing these jumps if it's really compact, because the JVM does inlining, and then it says, oh, well, we're just creating something, and then we're jumping over here, and then it goes away again, and it just collapses it into a jump. And so that's nice. And when it's more complicated, I couldn't get a good example to come up on this graph here, but it's about 10 to 20 times faster than a stacked exception. And so the reason that that's interesting is that when you're thinking about fraction of errors, exceptions are really, really expensive. So you kind of don't want to use them unless you're sure that you think your errors are really rare, or it's an emergency, you need to do something drastic. But if you can use Stackless exceptions and push the crossover point between the sort of exceptions which get worse and worse the more errors you have, and the boxing which doesn't, if you can push it over to here, there's a whole range of problems where you can address this other way, and you don't have to feel that it's going to be a performance nightmare. Okay, so it's fast, and then there's that caveat that I gave you. Okay, so now we have the outlines of a solution to this problem. Inside our library, where we really can pay attention and write unit tests, we can use error codes. Outside, we use Stackless exceptions, and we've got two problems. One is, how do we make them safe? And the other one is, how do we manage mutability? Because now with these error codes, we've got some sort of thing with some mutable state inside it, and it's going along, and we might want some help with that state changing. Okay. So in order to keep the Stackless exceptions under control, we can use something that I call a key pattern. I don't know if is already a known pattern, but the idea is this. So you have some class, and it can do safe things, which aren't going to throw a Stackless exception. And then it can do dangerous things, which are going to throw a Stackless exception. And the way that they throw a Stackless exception is that you give them a special key that they will use to throw that exception. So unless they have this key, you can't call that thing, and so you won't do it by accident like I did in the break example. And so what is this key? Well, if you have something which you parameterize by the type of this very instance of the class, you can have something like this, where you have some sort of supervisor method, which will, in this case, catch the Stackless exception. You can loan out this key to some closure that will take the key, produce a value, and you will give the value back. Or in this case, you probably won't have a default. If this was an exception, you would probably want some either type here. And so this solves the problem. Now, whenever there's a little bit of a penalty, which is anytime you want to use this foo class, and you need to use the unsafe functionality, you need to pass it in as an implicit. And so this is it adds a bit of boilerplate, but it only adds it once. So if you're going to do one unsafe thing, then it's a big burden. But if you're going to do them over and over and over again, the implicits take care of the rest. So Conceptually, it's just like checked exceptions, because you must handle them, or you must indicate in the signature that you know, that you got this capability, and since you have this capability, you're dangerous. But because we have an inversion of control here, where you're passing something in, you can pass in information that can help keep things straight, like the type of who this is. So with checked exceptions, it's you know, because generics are erased, it can get a little bit difficult to manage when you have individual types, you know, coming back. Here, I think it works more cleanly. Okay, and so just to see how this works, if you get some foos, and sorry, I messed up the name here. But anyway, so if you get a couple of foos and you have you call the supervised method on this foo, and you get your key, you can use the unsafe operations directly or in these methods. But if you try to use some other thing that might not be catching what you want, it won't compile because it's not typed properly. Okay, so that's nice. So we've got our stackless exceptions, which have given us a bit of a performance boost. Now what about mutability? So we were also proposing to use mutability under the hood to keep track of errors and other stuff like that. And so CPUs do this all the time. If you go call something, you push your registers onto the stack, you call them, and then you pop them off again. Okay, so that's as long as you don't have too much state, it's very fast and easy. So why don't we just do the same thing? If we come along to a case where we know we like our mutable state, we will have something where we can take our state, just save it on the stack, and then do whatever it is we need to do where it might mess up the state and then get the state back again. So that's the pattern. That's the pattern here. So if you take these two ideas and you stick them both together, you can actually get something which goes a pretty long way towards solving the parsing problem that I outlined before. So I'll show you a little bit about how it works. So I've called it Grock. It's like an iterator for parsable data, and of course there's all sorts of iterators for parsable data. This is one of the main ways you deal with it. But it lets you safely be optimistic and just go out and grab everything that you want, put it together in the shape that it's supposed to be, and then arbitrarily far on the outside, it'll catch what went wrong. So here's an example. So we're going to grok this string, 4 and 20 blackbirds. And so we take this instance, the apply method is the thing that gives us our key, which we'll call fail, but we don't need to really refer to it again. It'd be nice if the compiler would let us just not pay attention to this, but that's another bit of boilerplate that I can't get around without macros or something right now. So anyway, so we say, okay, well there's a 4 as an integer, so we'll grab that. Then there's some token, we'll grab that. Then there's another integer, we'll grab that. Then there's another token, we'll grab that. Okay, so you can run that, and it gives you an answer. Yes, it worked. 4 and 20 blackbirds, and it's typed appropriately. You can see over here it's typed appropriately. Okay, that's nice. Well, what if we do this? Oops. Then it says, oh no, that's no good. Error in integer, improper format. Okay, so that sort of seems like it's working as designed. So let's do a test. And so I could do a test on like my tracker, some of my scientific data, but I thought I'd use something that you guys are a little more familiar with, which is JSON. And so the JSON specification is really simple. It's one of the reasons it's nice. So you can have a value, and it can be any one of these things. And if you want to implement this in Grock or in other things, you basically just have to list those things. So here we go. We're going along. This could be dangerous. And we're going to peek at the first character, and if it's a brace, then we parse an object, and if it's a bracket, we parse an array, and if it's a quote, it handles parsing of quoting internally because it's annoying to do that by hand and not so fast. And if it's a number, if it looks like it might be a number, it's going to parse it into a D is for decimal, and if it's T or F, it's going to parse that into a Boolean. It'll get the rest of true and false. That's also built in. And otherwise, it's going to fail. If it's not any of these things, it'll just fail with some saying that there's some custom error. And so here you're actually using you're throwing the stackless exception here. So that's what this applying on this Grock hop thing actually does. So G will build an error that you can then pass in here, and you can throw it. Okay, all right, so that looks simple enough. Whoops. So I'll just go through the rest quickly. Okay, so we've got an object implementation. It's a little bit annoying. It's not as simple as this, but it's not too bad. You look for braces. Inside you look for things, which are quotes, and then it's a colon, and then you parse an any. Arrays, same deal, bracket. There's a little bit of bookkeeping about whether it's first or not the way I've done it, and then you parse any's inside. And the quotes are just quoted, and the numbers are just decimals, the way I have it right now anyway. And then you've got a little bit of boilerplate, you've got a few imports, you've got to, if you want to parse a byte array or a string, you've got to do Grock text byte array or just Grock of the string. And then if you are going to parse with that thing, you set so that you will eat an arbitrary number of white space delimiters. That's what the 0 means, and then you just go do it. So none of this is terribly bad. So you've got a complete, not very, it doesn't package your data very nicely, but you've got a complete JSON parser in about 40 lines of real code and about 10 more of this kind of boilerplate. That's not too bad. I mean, you can do less with something like parboiled too, but. Okay, so yeah, but anybody can parse JSON. So here's for example pretty much the whole thing there. This is more expanded than it needs to be, so that kind of hurts it on total number of lines of code. And parboiled too is great, by the way, especially if you have more complicated parsing tasks, because it uses macros to compile things efficiently. But the nice thing is that it works, right? So we took a Grock, which is supposed to be used for just parsing whatever thing you want to grab, and we took that approach where we just go in with JSON, and whenever there's something there, we just kind of grab it and stuff it into our builder, and it works. And maybe I should show you that it actually works. This is one of the examples on, I think, the JSON site about what a proper JSON is, and I've stuck it into something called pjson, and if you enter it, you get something that says, okay, so I've got my own either type for reasons I won't explain here, but anyway, so it says, okay, we got one, it was a yes, and it's a map from all this stuff, right? So it's just, yeah, it does do like what you would expect. Okay, so then the question is, how fast is this? Because one of the problems with when you're doing parsing is that there's this kind of dichotomy between this carefully hand-tuned parsers like Jackson, which is really fast at parsing JSON, and then you have these generic things like, for example, the most generic and with not much of an eye to performance is like the Scala parser combinator library. And so the question is, and the performance is much worse. And so the question, well, where does that, where do you fall on this spectrum? So if you try to parse that JSON file that I showed you, which is mostly string, mostly maps, and the leaf nodes are mostly maps from strings to strings, you get about 0.5 megabyte per second throughput on my laptop. And if you parse an array, it's a little of numbers, half integers, half doubles, it's a little bit better, 3/4 of a megabyte per second. But that's not very impressive compared to Jackson, where it just tears through this thing at 200 something, and the numbers is a little bit slower, mostly because parsing doubles is kind of annoying because you've got to convert decimal to binary and stuff. So anyway, but it's a huge improvement, right? Like 400 times or 60 times or 70 times or something. Okay, so where on that spectrum do you get? And this is where. it's almost at the Jackson speeds for building this tree. And it's considerably faster than Jackson for parsing the arrays. So how did that happen? Okay, so first of all, I just want to highlight that this is not what you normally see when you're doing parsers. So for example, here's a benchmark that somebody who I should remember who it was, I think it was Matthias, but I have forgotten, on this thread on the parboiled2 mailing list. And so here are parser combinators. They take forever to parse stuff. And I didn't look in the details of this benchmark, so I'm not sure exactly what's in it. But anyway, it takes forever. And the parboiled1 parser was way better. And the parboiled2 parser is way better than that. And then sort of these native things, and then Argonaut, and then Jackson. I mean, this is not an unusual thing to see for JSON parsing. You know, Jackson is pretty fast. So what's the trick? Well, part of the trick is that Grock is meant for direct parsing. You see data, you grab it, and you put it where you want it right away. You don't build up this structure about how to parse it. That structure is very helpful if you're having trouble figuring out how to parse it. Building that structure can really help you out. So because you explain the structure of the parsing separately from how to deal with the data, right? You need to separate those when it's a hard parsing job, but when it's an easy parsing job, you know, I've got it, I want it, let's just put it where it belongs. Okay, so that's part of it. And then so that's why with the things which are mostly strings that it's close. Well, plus I have custom quoted string processing code. So, you know, that's you know, not a negligible amount of the job. And then I wrote custom double parsing code, and the reason I did that is that I had to. And the reason, well, I didn't absolutely have to. I had to write custom integer parsing code because the Java library doesn't give you a good way to parse an integer without exceptions unless you know that it's already within bounds, at which point you've already parsed it. So that's not so useful. And I figured while I was at it, the double parsing algorithm is this sophisticated beast that keeps track of fractional error and does all of its computations while it's going and pushes it along and handles arbitrarily long numbers of digits before it even really knows how many digits there are. It's a really nice algorithm, but most of the time that's not what you have. Most of the time you have something which is no longer than about 16 or 17 digits because that's what you get when you do, you know, a print on a double. And so if you take that and you work out, well, what are the error bounds? How much do I need to know about which decimals and so forth? You figure out that you can do it with like 1 long's worth of input and 2 long's worth of, you know, conversion factors and do some multiplications, and ends up actually being quite a bit faster. So anyway, so that's how that got considerably faster. Okay, but now what about errors? Because this is all not going to be very useful if you get an error and it's just unintelligible. So this is what Jackson gives you. It says if we let me show you what this is. What did I call it? Broken JSON. Okay, so somewhere along here. Well, I don't know if it happened yet. Somewhere along here I put in a semicolon. Oh, here we go. All right, so this is hard to spot by eye. This is why you need parsers to do it for you. Do you see that? That colon turned into a semicolon. I don't think your data normally would have that problem in it, but anyway, so that's not going to work. And it's not part of the specification, and Jackson very helpfully says, okay, there's a problem with the colon is missing, and this is where it is. Not bad. And Grock does it slightly differently. It says, okay, this is token 21, position 124. It points you right where it is with a little bit of context. For what I do, this is more useful to me. And I should mention, I forgot to, or quasi ran out of time to put up the performance of these things. And as you would expect, the Grock version is faster by about 5-fold on the case where you just give it junk, and it very quickly realizes it's junk because of the difference between using exceptions and using full exceptions and stackless exceptions. But what if you want more context? So if you have some data, sometimes the relevant data isn't the stack trace because you don't care where in the code it broke. It's your data that's wrong. Your code's okay, your data's wrong. You want the stack trace for the data. So what do you do then? Well, most of the time you just go and hope that whatever tool you have gives you the information you need. But with Grock, one thing that you can do using this sort of mutable, sort of catch and preserve the state and then on a stack and then let you keep working, is you can do something like this. So I should point with a pointer here. So if you look up here, we've added to this array parsing thing this gContext thing. And what this does is it takes a by-name parameter that it will pass in to add an extra level of error reporting. So it will capture the context of where you are in the array. So it'll tell you the index. If this stuff in here goes wrong, you'll get an extra line in the output telling you about where you are in this index. And so this is a lot. But if you run that same thing now, where you do this both to the object and to the array, it points out exactly where it went wrong. So at the very bottom it says, okay, look, this semicolon is wrong. And look, it's inside this object. Here's where the object starts. And it's inside this object. And look, it's inside this array. And look, it's inside this object. And look, it's inside this object. Right? So it just steps through, because this is what you asked it to do. It steps through when it unwinds from all of these all of this recursion. As it unwinds, it adds onto this chain of errors, and so you can find out exactly where and how things went wrong in the data. Okay, so that's pretty much what I've got. So conclusions: non-local error handling lets things be simple. It can be fast. And at least for me, using a tool like this, parsing is only as hard as it ought to be, not as hard as it previously was. Now, I should also say, this is still pretty alpha code. I'm like rearranging things all the time. So, for example, do you want your stackless exception to carry a payload, or do you want, when you launch it, to store that in the parse object, right? There's a decision to be made there, and I made it one way that it carries a payload, but I haven't fully convinced myself that it's the right thing to do. And there are bugs in there. It's not too terribly hard to find bugs, but it's getting pretty close. So if you think this would be interesting or useful for you, you can send me an email. You can follow me on Twitter. I never tweet anything, ever. I have never, ever tweeted anything. And it's tricky, too, because I've got these underscores on the outside. And for example, if you look at your program, the trailing underscore is gone. But I will send one tweet at least and announce when it's ready. So thanks, and I'll take questions. So the reason is that the reason is I want it to be interactive. And so the type of data that I'm using, it usually takes about 30 seconds to get the data in. And when I'm sitting there waiting to check something or tweak something, the difference between 30 seconds and a minute is something that I feel.
You mentioned two mechanisms. The other is to handle mutability, but I didn't see the mutability in your code.
Yes. Okay. So that is here. So I was. So let me. So here's an example input file of the data that I actually parse. There's a bunch of numbers. Space delimited, and sometimes there's weird little stuff on the end of the strings, which makes it annoying for ordinary parsing. And so the mutability, where the mutability comes in, is here. If you want to parse this thing, I think I need to scroll down here to see the key part. Yes. So if you want to parse these lines and pack it into an appropriate data structure, whoops. Let's see. This is part of the mutability thing. So here's an example. I haven't used much obvious mutability inside. But this sort of is a meta uses usability. So this Grock each thing will break on the delimiters that you had before, and you give it a new subdelimiter to break on. So for example, you have files which are delimited by new lines. The lines are delimited by new lines, but within those lines you want to delimit by spaces. That's what I'm doing here. Okay, so what this thing does is you give it this this delimiter, you just go in and you directly parse the line. You say, okay, I'm going to just pack all this stuff right into my line data structure. I saw there was an integer, and then there was a floating point number, and a couple of integers, and then there's 11 integers, so I'm just going to grab them all in. And then there are these various percent escape things at the end, which we can read. But the thing is, if you fail here, you're going to leave your parser mutable state randomly in the middle of whatever was failing, and that's not what you want. With something like this, where the lines are independent, you want to back out and say, whoa, I'm just going to go to the next line. And so that is what Grock each will do. It pushes that information onto the stack, and it recovers in case it throws an exception. Yes?
So you can do independent lines and lines which are not.
Right. So the default is you just consume data, and wherever you end up is wherever you end up. And if you have some way to stop yourself at the end of a line, and that's fine. And if you go on for 2 lines, that's fine. If you write for example, a CSV parser with it, so one of the tricky bits with your parsing CSV is that you can quote a new line in the middle of quotes, right? And so you do your normal thing where it's like, I'm going to eat to the end of the line and then I'm going to parse it. It's like, well, it's that now you have this gluing problem, where the quote goes across. With Grock, it doesn't happen, partly because it happens internally, that the quote parser works so that doesn't happen. But more generally, when you're doing subparsing, you actually can parse. So if you just switch which token you're parsing on, then you'll just eat the other tokens. And so that's basically how it happens there. Yes?
Can you do practice tracking?
Yes, so that's another part of the mutable state. So for example, all right, so let's suppose we go, all right, am I going to even remember, what's this called? It's called, did I call it attempt? All right, so we're going to attempt to parse a decimal here. Let's see. Right, and so if it doesn't work, it's going to keep going. So we're going to do the attempt, and in this case, since I know it's just going to, well, we'll just do it, okay? And it gave us a no here. But normally, if you hadn't done this, it might get some way in and then fail. So let me change it so it's 0.this, okay? So that's not a valid double. And it says, okay, look, you screwed up. The t is not, you've got some improper format in your real number. And okay, but then if you didn't use this attempt thing, when you tried to go back and parse, you'd be on the t. But if we do this again and we just try to take a token, because we attempted it, it gives you back the full token. So it remembered the state. So that's how it works right now. Obviously, you could have a different one where you try alternatives until one works and various stuff like that, which I had and then took out, and maybe I should put back again. That's right. It does by nature do streaming, yes. So one thing that I haven't done that isn't ready yet is, so there is one tricky bit. Some things have no particular predefined length. Like, for example, a quoted string could be 10 characters, could be 100 million characters. They're both valid. If you could parse them, they'd fit in memory. So the question is, if you have something which is streaming, where you either actively need to go get your data or you need to wait until your data is there, do you want to add that logic in your basic string quoting thing to say on every character or in some sort of blocked structure, you know, I don't know how far I'm going to go, so if I run out, I'll go try to get more. And so the way that I'm planning on handling that is to go back and use these either the stackless exceptions or the error codes that are produced depending on which I need. Because then you can say, okay, just go, I'll tell you where the end is now, but if I'm a supervisor, sort of if you have a sort of a worker Grock inside another one, the supervisor can say, okay, it hit the end of what I gave them, but I actually know that, you know, I can pull more data from disk, or, you know, if I just wait for another, you know, second, I'm going to get more data from the network, and then it will relaunch that same thing with additional data. So that's the idea, at least for files. I'm probably not going to bother doing this for anything truly streaming with time delays and so forth, because I don't have a need for it right now, but it's doable. When I get the file stuff done, you could just follow the same template.
Are you going to split this out into a separate library? Let's see right now that it's part of your KSD.
I don't know. If you think the answer should be yes, then sure. But I would argue that I'm trying quite hard to keep everything in that library to be relatively useful. So I don't think it's necessarily bad to pull much of it in. And if there's some functionality that I duplicate that is, you know, elsewhere, then I'm very receptive to the idea of just dropping that out of KSD entirely and saying, look, the standard is we use whatever it is, you know, cats or algebra or whatever, right? This thing is handled really well there. Everybody should standardize on that, even if they're two competing things. You might be able to convince me, you know, that that's the way to go. So maybe I'll split it out, maybe not. But, you know, if enough people want it, sure. Okay, thanks, let's get to lunch.